right, let's talk about isometries. Yes. Okay, we are going to understand and use the definition of isometry. Okay, so an isometry, this is a transformation that involves moving all of the points that make up a geometric figure according to the same rule. Okay, the original figure is called the pre-image. It feels like there should be a hyphen there, but there isn't one. And the transformed figure is the image. Okay, an isometry is a transformation that does not change the shape or size of a figure. Reflections, translations, and rotations, they're all isometries. Isometries are also called congruence transformations or rigid motions. So those are all synonymous. They're all synonyms. Okay, isometries are going to change the position of a figure without changing its shape or size. That is to say, the pre-image, that's the before, and the image, that's the after, they are congruent. Okay, so these are the reasons that the image and the pre-image are congruent, because in a rigid motion or an isometric transformation, we preserve distance, we preserve angle measure, we preserve betweenness. That is, if a point is between 2 points, it's going to be between those same points in the image. It preserves collinearity. So if points are collinear in pre-image, they're going to be collinear in the image. Okay. So here are some examples of transformations. The ones on the left are rigid transformations or isometries. And then on the right, we have a dilation, which is non-rigid. So let's talk about the rigid ones for a minute. The first one is a translation or a slide. And if you remember from Algebra 1, we had another name for this. It is a shift. We would do a horizontal shift from side to side or a vertical shift up and down. With our parabolas, with our exponential functions, we would shift linear parents upside down, not upside down, up and down. Okay, so this is a shift. Okay, rotation or a turn. Okay, we saw a little bit of this in our last set of notes with the symmetry. When we rotate about a point, we're going to do a lot more on rotation in future sets of notes, but that's an isometry because all of the angles are kept and all of the lengths of the sides are kept to make congruent figures. Okay, reflection. We did a lot of this in Algebra 1 too. When we had our parabolas, we did a lot of reflecting in the x-axis. Okay, we did flips in the x-axis. This one looks like it's been flipped in a y-axis, but you should be familiar with the idea. All right, last but not least, we have dilations. These are the non-rigid transformations. So these don't produce congruent figures, but these figures are what we will learn are called similar. Okay, so the cool thing about similar figures is that these corresponding angles are congruent, the ones I'm marking. Okay, but the side lengths changed. So we will talk a lot about that in a future unit too. But for now, we just know that a dilation is non-rigid and it's going to enlarge or reduce the original figure. So you can think about like pupils being dilated. You know, they get bigger. They're still round. Your pupils are still round. You don't turn into an alien or like a cat, but they get bigger or smaller. An alien or a cat. Okay, so for each of these, we have to say what type of transformation and then tell if it's an isometry or not. So for this, we'll say yes or no. And then for the type of transformation, we will name it. Okay, so for my first one, you can see that this just scooted over a little bit to the right. This is a translation or a shift. Okay, all the angles stayed the same, all the side lengths stayed the same. So this is an isometry because those figures are congruent. Okay, next up, you can see that this figure got rotated around that point. Okay, so this is a rotation. But it's the same size, it's the same shape, those angles look the same, the arc lengths are the same. So this is also an isometry because it produced a congruent figure to the pre-image. All right, check out this one. If I draw a line down the middle, an axis of symmetry, if you will, you can see that this is a reflection. Okay. Ooh, or it could be a rotation. I forgot to say that in class. Okay. Well, maybe I'll bring it up tomorrow. So we could also like rotate this about that point. Okay, so reflection or rotation. That's a fun one. It would have to be a rotation of 180 degrees, right? Okay, but either way, it is an isometry, so yes, because those are congruent figures. The next one is a dilation. Oops, that's not a D. Dilation. And you can see that these angles are going to match, but the little red pentagon is obviously smaller than the blue one, so this is not an isometry. So we're going to say no, because they're not congruent. Okay, next we have another translation or shift. Okay, and this is an isometry because those figures are congruent. Okay, this one's kind of a thinker. It was easier to see when it was like sideways, but I rotated it. It makes it a little harder. This is actually a reflection in a horizontal line of symmetry. Mm-hmm. So this is a reflection. And it is an isometry because those figures are congruent. So what we're looking for in these reflections is that whatever point was here ends up there. It's the same distance away from the axis of symmetry. So this point here, its perpendicular distance is the same as this point here, okay? That's what we're looking for, is that those lengths match. All right, here is another reflection in a different axis of symmetry. And this is an isometry because those are congruent figures. All right, this set of triangles in the middle here, this is not. This is a dilation. The red is smaller than the blue. Not, because they are not congruent. Okay, here we have a rotation about a point. Okay, and this is an isometry because they are congruent figures. All right, last but not least, these kind of look like crazy little bunny rabbit heads. This is a reflection in that line of symmetry. And this is an isometry because those crazy bunny heads are congruent. Okie dokie. A transformation maps a figure onto its image. When it says maps onto, that means that it coincides with the image, and then it's indicated with an arrow notation. So whenever we see that arrow, that means a transformation happened. It's like an event, okay? So an isometry gets an arrow. Dilation gets an arrow. The prime notation, the little apostrophe, that's used to identify image points for the first transformation. So if only one transformation has occurred, that's the prime. The prime notation tells which one is the image, as opposed to the pre-image. Okay, if we do double prime, that means it's been transformed twice. So that's the image of the image, or the second transformation. Okay, so for example 2, we have to pick the diagram where quadrilateral ABCD has been reflected in line N. So remember about that perpendicular distance. What I'm looking for is that if I drop a line from B to my line of reflection that's perpendicular, I should have that same distance away a point B. And here I don't. The only one that's close is C prime. Sorry, that was B prime. C prime, okay? This is not mapping at all. Okay, look at A. A, well, A is kind of close. Actually, that was a bad example maybe. Look at D. Okay, so D, that one should go like right here. This should be D prime. Okay, but that's not where D prime is, so this is no. All right, let's look at another one. So, perpendicular distance to D, okay, go to the other side, same distance away. D prime should be here, but the closest thing there is B prime. Okay, this does not look good. So this one's a no. All right, next. Same perpendicular distance away on the opposite side. C should be here, C prime. Okay. D prime should be here. A prime should be like way the heck out here. So all of these are in the wrong spot. This is a no. Wouldn't you know I made it the last one? Of course I did, because I wanted to talk about all these other fun examples. All right, last but not least, same perpendicular distance away. There's our C prime. Okay, here for B, B maps onto B prime. Perfect. Okay, same perpendicular distance away. A maps onto A prime. And same thing for D. Okay. D maps to D prime. So this is the winner. Yes. Oh my gosh. That's a crazy face. Okay. All right. For this one, we have to name the pre-image and image points for the triangles. We have to list the corresponding angles and also the sides of the angles. So the way this is going down is we have to look at this rule. This rule is telling us what's happening. Remember that this little arrow means that we have a transformation. Oops. Okay, that one kind of got away from me. So we're transforming triangle ABC into triangle A prime, B prime, C prime. Okay, but the order is really important because A is mapping onto A prime. B has to go to B prime, and C has to go to C prime. You can tell by the order that the points are written in. Okay? Okay, so let's do this. Point A gets transformed into point, oops, not point, point A prime. Okay, we said point B gets transformed into point B prime. And point C gets transformed into point C prime. Okay, we get all that from the order in the rule. Okay, now we have to list corresponding angles. So angle A gets transformed into angle A prime. Angle B gets transformed into angle B prime. Angle C gets transformed into angle C prime. You guys seeing a pattern here? Okie dokie. Now we have to do corresponding sides. So if I look at this short little AB side. Okay. Side that is segment AB gets transformed into segment A prime, B prime. Segment BC gets transformed into segment B prime, C prime. Segment CA gets transformed into segment C prime, A prime. Wow, that was a lot for my little brain. It's just a lot to make myself say while I'm writing it. It's fine. Okay, so what kind of transformation did we get? Well, speaking of reflections, I see an axis of symmetry right here. C got reflected to C prime. B got reflected to B prime. Okay, and A got reflected to A prime. So this is definitely a reflection. Is the transformation isometric? Yes, we know that reflections are isometric because we preserve the angle measures and segment length. That means those figures are congruent. If we get congruent image and pre-image, that's an isometry. Okay. All right, corresponding angles. We should really start with the order that they go here. So we're going to start with E. Okay, so they're telling us in the rule that E maps to E prime. So that means that angle E has to map to angle E prime. Whoa. Okay, we also know then that angle F will map to angle F prime. That angle G must map to angle G prime, and the angle H, angle H will map to angle H prime. Corresponding sides, just like we did with the triangles. Let's start with segment EF and work our way around. Segment EF, that's this one. You can see that it has to map to E prime, F prime, maps to E prime, F prime, the segment. Okay, then we go to FG, the segment. FG, the segment, maps to segment F prime, G prime. Okay, we keep going. Segment GH maps to segment G prime, H prime. Segment HE maps to segment H prime, E prime. It's not hard to do, it's just hard to say. Okay, so question is, what is the image of G? So G is the point right here, and it maps to G prime. So point G prime. Okay, what is the pre-image of H prime? Well, H prime is here. Its image obviously had to be point H. Okay, what transformation was performed on this pre-image to get the image? Well, it didn't get spun around. It didn't get reflected in an axis. It just kind of got slid, right? So this is a translation. And this translations are one of our isometries. So we say yes. Okay, the angles stayed the same. The segment length stayed the same. These figures are congruent. Okay, I was getting really tired of saying prime, so I'm very pleased that I don't have to say prime for this example. We can still tell what goes to what by the order. We can see that N goes to S, I goes to U, and D maps to P, okay? That's gonna be our guide. All right. So angle N maps to angle S. Angle I maps to angle U. Angle D maps to angle P. Hold on. Okay. For our sides, we have to make sure that we keep going in order. So I'll start with NI. segment NI maps to segment SU. Okay, that's this one going to that one. Next. Do that. Okay, then ID, segment ID maps to UP, the segment. So ID is here, it goes there. Okay, then DN maps to PS, the segment. Oops. DN, PS. So you can see that this has been rotated. Okay, what is the image of D? Well, we can tell by the order. If D is the last thing in the pre-image, then we look at the last point in the image. So that would be point S. What is the, nope, that's P. Point P. Okay, I think I just looked at this S and said S. Okay, look for the pre-image of S. So if S is the first thing, we want the first letter or point in the pre-image. So that would be point N. Is this transformation isometric? It sure is, because these figures are congruent. We didn't have anything dilated. Oh. Are congruent. Okay. Now, I didn't realize that this had another page in class today, so I didn't even print this. So I haven't done these yet today, so we'll see how I do. Okay, we have to find the value of each variable given that the transformation shown is an isometry. So this is really important. That means that all of the lengths and angles have been preserved. So as long as we know what maps to what, we can solve cute little fun equations and figure out our variables. So if I look at this, I see angle I maps to M because they're both second, and angle M is 90 degrees. So I know that 15y has to equal 90 degrees. So if I divide both sides by 15, oh, I think it's 6. I think y is 6. I'm getting a calculator. Okay, it's 6. I didn't embarrass myself. Okay, the next thing we need to know is how to find x. So look at JK. JK is going to map to NO. So those two have to be congruent. So we can say that 3x equals 18. Oh my gosh, this one's 6 too. That's weird. Okay, notice that we did not even use this 24. That was just put on there to confuse us. But we didn't fall for it. Okay, so looking at this rule, I'm looking for angle B. Oops, that's not the right symbol. Angle B. So B should map to E. These two should be congruent because we're told that this is an isometry. So we know that 5y equals 30. Oh my God. This is crazy. Okay, so when I divide by 5, I get y equals 6. Okay, I'm pretty sure that these examples might be possessed. If I start spinning and like my head starts spinning and like green vomit starts coming out of my mouth, like get a priest or something. Okay, next we want segment BC. BC has to map to EF. So we know that 2x plus 4 equals 20. Okay, this one's not going to be 6. I can tell already. Subtract 4 from both sides. I get 2x equals 16, and x is 8. All right. Ooh. Okay, we're fine. We're fine. All right, so they're giving us an axis of symmetry. Okay, so that means that C maps to Q, B maps to N. I hope these colors are helping you. They're helping me. D maps to P, and A maps to O. Okay, while I paused it, I changed my blue dots into green stars because the blue and the purple looked exactly the same and it confused me. Okay, so, woo-wee. Where do we start? Okay, I see something we can solve for. Look at this side that's 10 units long. It came from this side over here, which is 1/2 z. So I can write an equation for that. I know that 1/2 z equals 10. So if I multiply this side by 2 and this side by 2, my 2's cancel and I get z equals 20. Okay, that's one down. Oh, okay, here's something important. If this angle is 95, it's marked congruent with this one, so this is 95. Oops, degrees. Okay, and I know that angle B, has to be congruent to angle M because one is the image and one is the pre-image. They have to be congruent if this is an isometry. So 3x plus 35 must equal 95. Subtract 35 from both sides, I get 3x equals 60. Divide both sides by 3, I get x is 20. Oh, if these are all 20, crying out loud. All right, next. Oh my goodness. Okay, I'm seeing that this guy and this guy have to be congruent because they're image and pre-image. Okay, so we know that 2/5 W has to equal 20. So I can multiply both sides by the reciprocal of 2/5, which is 5/2. 5's cancel, 2's cancel, leaving me with W. Okay, 20 times 5 is 100. Divide 100 by 2, W is 50. Okay, we just have to find Y. Okay, I guess there's no time better than the present to tell you that the sum of the interior angles of a quadrilateral is 360 degrees. I don't know how else you have to know that to solve this problem. So I'm telling you now. So all of these interior angles have to add up to 360. So we figured out that this one has to be 95, and so must this one. Okay, so far we've got 95 plus another 95. Okay, we also have 110. Okay, what does that add up to? 5 and 5 is 10, carry the 1. 18, 19, 20, carry the 2. Okay, I've got 300 degrees so far. So this last angle, if I'm adding up to 360, has to be 60 degrees. That was a lot. This problem was a little brutal, sorry. So 2y has to equal 60 because these angles have to be equal. Congruent. The angles are congruent. The measures are equal. So y is 30. Whew. Okay, sorry about that last one. Yeehaw.